So this week we were continuing off of the previous chapter. Where we kind of left off was we had the metrics and we saw that the performance it was getting at surface level, you look at it and you go, oh wow, 99.97% accuracy, that's pretty good. But then they showed us the different metrics and we saw, oh, actually it's just always guessing that every object is not a nodule. And so it turns out that's not a very useful classifier because we could just do that on our own. We don't need a neural network to tell us that. And so what we're doing in this chapter is we're looking at the different metrics we can look at in order to measure that phenomenon. And then we also looked at some techniques in order to fight that, in order to create a model that actually converges well and doesn't overfit to the very small number of positive cases that we have. So that's the first section, the 12.1. They just basically laid out, here's our problem, this is what we're trying to solve. And then in the second section, they're looking at, they used an example of good dogs versus bad guys. And they have the two dogs, and one of them has a whole ton of false positives, and the other one has a whole ton of false negatives. And so they define those terms. So a false positive is basically, they have the one yappy dog that is constantly concerned with everything that goes past. And so it's classifying everything as positive when it should actually be negative. And then a true positive is when they actually correctly classify a burglar as such. And then a false negative is the opposite, the dog that is sleepy and not attentive. And so every once in a while he detects something, but it's not that often, is missing some. And so the example of a false negative is a burglar gets in and nothing's detected. And then the true negative is there's nothing going on and nothing is detected. So that's the four different pieces of what typically makes up the confusion matrix that they didn't touch on, but I think is probably important to at least mention. Any questions on that section yet? That's pretty fundamental. The rest of it relies on that. So moving on to 12.3, graphing the positives and the negatives, they showed a whole bunch of different visualizations. It's kind of hard to summarize exactly what they're showing. The core concepts they're showing, though, are recall, precision, and F1 score. And recall, they've got the formula, but I think the more human definition of it is that you're looking at the percent of the positive labels that you captured. So you probably want a high recall when you are discussing burglars potentially, because you don't want any burglars to go undetected. But if you have so many false positives, I need to make sure I say this correctly. I always screw these up. So it's true positives over true positives plus false negatives. So you don't want to potentially miss any burglars. That's the false negative portion, and so that's the recall side of things. And then in terms of precision, you don't want so many false positives that the signal is no longer useful. So in theory, you could have a dog that's just always barking, but that's not a useful signal because it never actually, the percent of alerts that are interesting to you is very low. And so that's what precision is capturing. So if you ever have a classifier that only guesses a single sample positive, but it gets that correct, it's got 100% precision. And so you have to balance the two, the recall and the precision, to get anything that's really useful, because both of the metrics can kind of be played. You can get very high numbers on both of them if you just tune your threshold correctly, basically. And so the metric that a lot of people use that kind of summarizes the two of those and gives a good combination of them is the F1 score. And that's looking at the multiplication of them over the sum of them. And that gives you a good summary. So you can't necessarily exploit just one side or the other. You need to be good at both in order to get a good F1 score. And so a lot of people use this metric in
I have
order
a,
to.
I have a question on that. Why 2 times the precision times recall in the numerator as opposed to just precision times recall? Is there any mathematical reason or any logical reason for that?
It makes it so that it can max out at 1 is the main factor. So precision and recall. So if we're looking at this side, precision can go all the way up to 1. Recall can go all the way up to 1. And so the sum of these can end up being 2. But then if you multiply them, even if you get perfect precision and perfect recall, it's just 1 times 1.
Got it.
And you end up
Got
with
it.
1/2. And so just multiplying by 2 makes it so that it can
So it
theoretically
normalizes
get a
it.
perfect
Got it.
score of 1.
Got it. Okay. Got it.
Yeah.
Yeah. Thank you.
Yeah. And there's other ways that you can rewrite this in terms of precision recall, and so forth. You can split precision back into its parts. So you could say true positives over true positives plus false positives, and you can see what the full breakdown is. But I think it's more simple to look at it as just precision times recall over precision plus recall.
Hey, just a really quick comment. So when you do the regular arithmetic mean, the average, right? You would just take precision plus recall divided by 2. So that's just so you know, like it's pretty common to have a 2 when you're doing any kind of average of 2 numbers, whether it's a geometric, a harmonic, or an arithmetic mean. All
True.
right. So that you don't. So hopefully that helps, so you don't feel like the 2 is a total hack. And then the way someone explained precision recall to me that for me always like really stuck is the reason why a lot of people think about precision recall versus like in medicine where we do sensitivity and specificity is imagine you're just doing a Google search. So precision says if you get 10 results back, how many of those 10 are actually related to what you wanted? And recall says of all the pages that were about what you wanted, how good a job did Google do of finding them? And so you can actually see, for example, that in the Google use case, typically precision is more important than recall. Okay, so in your top 10, or even if you click next in the top 20, you want those to be really related to whatever your topic was. But if there's 1,000 pages about transformers, Google doesn't need to necessarily know that I found exactly all 1,000 of them. I just need to give you 10, 20 good ones. So that's helpful for people.
Mm-hmm.
I always have trouble with sensitivity and specificity because I use those all the time in healthcare, and I occasionally get tripped up. But precision and recall, after somebody explained the Google search example, I never forget this.
Mm-hmm. Yeah, that's a good example. So moving on to 12.4, what does an ideal data set look like? In this chapter, what they're kind of educating us on is how to rebalance the data set. And what they're kind of describing is you've got 250,000 of the negative class, or even more, and you've only got 500 of the positive class. And in that scenario, you might go many batches before you even see a single positive example. And so what that's teaching your model is to completely skew towards the negative class. And so some people think about the rebalancing differently, but what they kind of mentioned is that in theory, you would still converge to the same solution eventually. So if you have 250,000 and you have 500 of the other, if you just keep iterating, you will eventually get a decent result, but you have to iterate through all of those negative examples so many more times than you actually really should, that you're just wasting compute power. And so what they're showing is if you increase the prevalence of those 500 cases that you actually care about, you will converge much faster because you're actually seeing the thing that you're interested in more. It's like if you were teaching a kid their shapes or something like that, if you show them square 65 times in a row and then you just show them circle once, you would expect they would learn square a bit better than they learned circle. And you know that they specifically don't know very much about circles, so you would want to show them more circles. And so that's how I at least think of the rebalancing. In some kind of introductory ML courses, a lot of people argue that you'll get better results, and I think that that's generally not the case. You just converge significantly faster, is what I've seen, at least in my experience. And so
the reason why they're saying that is because you can fall into a local minimum trap, and it's a lot harder to get out of it. You have to get really lucky on one of those iterations to have gotten just a batch that contained a lot of positive examples to push you over that that hump and get you into another area of the objective function.
Yeah.
I think also if you use scikit-learn, some of these other algorithms, if you don't have a balanced data set, you can just get a permanently not good result.
Yeah, because the optimizer isn't changing it's not an iterative process. Like those learners are closed form. They're done once they go through your data, whereas the iterative model, that we're doing for deep learning can go forever and keep trying and keep trying and keep trying with random samples.
Yeah, the underlying algorithm definitely matters too. So if you're just doing a linear regression, then it will probably have a significant impact. So you have to keep all of that in mind. It's all, you generally won't hurt yourself by balancing, but in some classes I've seen people claim it will do magical things, and that's not necessarily always the case. But in this case, when we have such an extreme imbalance, it significantly helps. Convergence is, I think, the overall thing they were trying to show. So one of the
sorry, real quick question. Is there, I guess, in general, a number when, because there are no data sets perfect for the most part, there's usually some sort of imbalance, but I guess to what extreme, where you have like 1% representation of your total, or I'm just kind of curious about just generally what people think.
I think it largely depends on the complexity of the data, because what you really want is your model to have sufficient examples and exposure to the thing that you're interested in. It's not necessarily so much about the ratio as much as it is enough exposure to this certain case. So I would say under probably 20% minority class is worth at least considering. But you don't really have to take action typically unless it's probably under like 5%, I would say. And in this case, they said it was like 1 to 400. So that's a case where it's just seeing so many examples that are negative that it's never seeing positive.
Thank you.
Yeah. So in the chapter, they're showing that you can use the weighted random sampler, and this is a really good function within PyTorch. The data loader can take a sampler, and there's several different pre-built samplers that you can plug in there. And the weighted random one, I tried using it on the lift competition, and I ended up not being able to use it for that. But the general premise is you can give weights to different classes, or you can give weights to different indexes. So you can explicitly say, I know that these certain rows are interesting, or I know that the positive class is more interesting than the negative class. And you can essentially make it change the prevalence of the different classes or the rows. The issue that I ran into in my use case was it actually has a limit on the number of rows that it can do sampling on for some reason. There's just some underlying limitation there. It can't go beyond a number of rows. And so in this case, I didn't entirely understand why they needed to do the custom code. I think it was because the labels aren't directly available in a certain format in data loader, but I'd have to look back at that. But they essentially made a custom one, and what they did in their custom one is they said, here's our list of negative sample rows, and here's our list of positive sample rows, and every batch we're going to pull in a balanced amount from each. And then one of the things to keep track of is you might want that on the training set, but you don't want to change the distribution on the validation set. You want your validation set to still be indicative of the real world distribution. You just want your training distribution to be different. So that's a common mistake that I've seen, especially on Kaggle. People go, oh, wow, I rebalanced and now I get this so much better score, but it's on a validation set that they've rebalanced and isn't really indicative of the future performance on real world data. So just something to keep track of. Any questions on 12.4?
I still have a question, maybe more related to maybe the kind of the confusion I have regarding the balancing versus keeping a relatively realistic view of the reality, like just by random sampling. Are we saying that the primary purpose of balancing is, I'm just trying to, in my head, trying to reconcile that, well, the benefit of balancing is to gain more, I don't know, maybe the precision or the accuracy of the prediction in the end. But let's just say that if we're trying to predict like the presidential election, right? And there will always be some groups that are, naturally speaking, minority groups or minority classes. So when you're training a model, you're trying to be more accurate in terms of predicting what they are going to do. And so you balance the sample and kind of, if I am understanding the concept even remotely accurately here, you're trying to give it a higher weight so that it occurs more often in your data. But in reality, the minority class only accounts for a very, very small share of the population. Their vote literally does not matter as much. So how do we go between these two things?
So I think going to the example that they were using, when we're looking at neural networks, it looks at a batch of a fixed size. So if we have a batch of 32 and all of the samples are negative, then that batch was essentially wasted because our model is already very confidently guessing negative on a lot of things. And it's not getting any exposure to the positive class that we actually care about. Carrying that over to your example, though, it's kind of the same idea, where if we're training a neural network that has that as some input and it has no exposure to Native Americans, for example, then it has a whole bunch of batches where it's just all of one class, and then it only gets one batch every 1,000 that has Native Americans, and it's probably not going to learn it very well, which is it's one of those things where if you look at the metrics of the different subgroups, you could say, wow, we're doing amazing on the group of white people, but then we look at the subset of the Native Americans and we can say, oh, wow, we get 50% accuracy or something like that. And so you can actually significantly improve the accuracy of your algorithm just by having additional exposure and making sure that it's actually training on those samples reasonably well.
So my question maybe is a slightly different one. So I get that, but wouldn't we say that, let's just assume right now, and I think it's still the case, white segment of the population is still the dominant segment of the population. In a mathematical way, if we do the math, their votes will still matter the most, right? And even though, yes, the model may be enhancing its ability to predict what Native Americans are going to vote, but if we look at the entirety of the population, the outcome of the entire election, would that do anything to the prediction of the entire election?
So it depends on what your objective is. Is your objective to predict the outcome of the election? If it is, then certainly the votes count to your algorithm or to your outcome in proportion to their ratio within your data set. But what Ryan is saying is that at some point you get really good at the majority class and you can't get any better at predicting how they're going to vote. But you can very easily and cheaply get really good at that minority class. So all the others that are not white. And when you do that, that will improve your outcome by simply adding to your model's accuracy overall and your ability to influence the election outcome overall. So ignoring your minority classes doesn't help you improve your accuracy. It improves your accuracy to pay attention to that minority class, and because it incrementally improves your accuracy. Yes, you'll move from maybe 90% accuracy to 91% accuracy, but it's an improvement that your competitors won't have.
Gotcha. Okay. So this is not necessarily reflecting when we use the model to predict the test data. It's going to also, and probably is related to the example that Ryan, you mentioned a moment ago. It's still trying to really predict the random, like it's the true distribution of the real world that we're trying to predict, even though now that you have incorporated a better performance for the minority group. Am I making sense here?
Well, if I could just sort of extend what Ryan and Hobbs said. So let's say you had sample data. I mean, in the real world, I don't know how you get this data, but let's say you just had data on 1 million whites and 1,000 Native Americans, and you just naively shove this into some algorithm, okay? Over time, and it trains, it's gonna, like Hobbs said, it's gonna do a pretty good job predicting those 1 million people, and it's probably not gonna do a very good job predicting those 1,000. Now,
and we agree on that. Yeah.
If those 1 million people break 60-40, you don't even need to know how those 1,000 people voted. So it won't break you not to have that, which I think is one of the things that you're thinking about, right? But the reality is your prediction would still be more accurate, like Hobbs said, if you got those 1,000 people right, in addition to getting the 1 million people.
You're right.
And every prediction has a confidence interval, especially when you're trying to predict human behavior. And so getting that extra 1% may be the difference between you falling across that 60-40 line or the 50-50 line or whatever it is.
And the more that your election isn't 60-40, it's 52-48, 51-49. Well, now you're really in danger because in reality, there's multiple minority classes. And so to the extent that you're all doing, poorly on all of them, right? So that's why what we're saying isn't that the minority class is equally important to the majority class in this use case, okay? What we're saying is for training purposes, in order for your model to learn, you want it to be equally important, and then you just use it in whatever your use case is, right? And so in the extreme, like for cancer detection, the minority case is the case that tends to be of interest, okay? But if you had something else where the majority case was the one that was of interest, and I mean, it's so nonsensical that I don't think I can even come up with with an example, okay? But let's just say, like, you're wondering whether or not smoking is bad for you, and there's this 1% of people for whom they could smoke like a smokestack and it would not hurt them at all. Like, it's just not really important, right? Well, all we care about is that the 99.99% of people smoking hurts them. Then you don't really, in that case, your case of interest is the 99%, not the 1%. So in that case, yeah, you're absolutely right. You could get away with having really poor predictions on that minority because that's not your class of interest. So
you'd still do better on those people because sometimes those people do get cancer.
Right. So what Hobbs is saying is you can have your cake and eat it. You can get just as good performance with your majority case and get better performance with your minority case. So why would you ever not want better over? You're not losing anything by getting better minority case performance.
Okay, gotcha. Thank you.
Yeah. So moving on to 12.5, looking at overfitting. We've kind of talked about this a little bit already. When you have insufficient number of examples, then you might end up with a scenario where your model has so many parameters that it can essentially just memorize the inputs and map them to the outputs. And then it's not really useful on new data. The example they were using is a detector that is trying to figure out roughly the age of someone based off of a picture. And they were saying basically, if you just learn, here's John, he's got a certain scar, his eyes are in this shape and this color, it can just directly learn, this is John, he's 55. And that's not really useful because your goal is to predict on new people. So it's trying to look at the general characteristics of maybe wrinkles, maybe gray hair, maybe something else. And so in that scenario where you don't have enough samples of something, you might have to find some alternate technique in order to augment your data and help it generalize. And so this is an area that a lot of people have had good success in. Moving on to 12.6, data augmentation. And so a lot of people think about this in terms of just random shifts and stuff like that. But the way that I try to think about it is simulating new scenarios that are realistic to your data. And so for a lot of scenarios, this could be simply mirroring your image. So if you have a view from one angle and you just look from the other angle, it's still the same person. It's still a dog. It's still a car. It's still a whatever. But your convolutions or whatever you're using will learn from the opposite angle now. So if you do see an example where something's flipped, then it will still work correctly. And so that's just simulating a scenario that our algorithm might not take account for. So a while ago, we talked about CNNs and how they're translationally invariant. So if something is anywhere in the image, it will detect it. But if it's flipped, then our convolution won't necessarily match that. And so what a lot of these augmentations are trying to do is create something that is invariant in other factors as well. So if you rotate it slightly, it's still a dog, it's still a cat, it's still whatever. And so we're trying to build robustness to those other scenarios too. So in this one, the examples, they said mirror left, mirror right. They also said mirror up, mirror down. I don't know if that necessarily makes total sense unless you combine that with also doing some other techniques. I'm not sure if they're going to talk about it at some point, but there's this thing called test time augmentation that might make that still be useful. And then they talked about shifting the image. I don't entirely understand that one because we're using convolution, so I don't think that that should really make a huge difference.
Hey, Brian.
Yeah.
I think what the author said is that they were shifting a non-integer number of pixels. So they were forcing it to reinterpolate on fractional shifts.
Yeah. Okay. Yeah.
Does that make sense?
Yeah. Yeah, that makes sense. I guess that makes sense. I don't know how significant that would be. I looked at some of the graphs that they had, and it was kind of difficult to read. They didn't have the best labels on it, so I couldn't directly see, oh, it looks like the mirror works well and the rotation works poorly or anything. It was kind of just a jumble of lines. But yeah, and so the other options they talked about is scaling up or scaling down. And all of these kind of make sense in the physical world. So if you have a person and you just find a different person that's slightly larger, their cancer is going to be similar. And so you can just look at this scaling up and scaling down, and even the imaging, so the rotation, so it was, how were they positioned within the scanner? Maybe they're just slightly rotated. And so all of these things are kind of just simulating different realistic scenarios that would happen in the world. and even adding noise. So you might have one scanner versus another scanner. This one comes out a little bit clearer than another one. And so you can introduce some noise to the scans. You can just know that there's always some amount of noise. So you might want to make it robust so that when your model is learning, it's not memorizing the noise, it's learning from the actual image. And so those are some of the examples of augmentation that are relevant to this scenario. In the lift competition that I've been working on, there's a lot of different things that we had to consider, because there's different stipulations. When you're looking at cars driving on the road and you flip it, that's not necessarily the same thing anymore, because that would be like we were in the UK driving on the wrong side of the road. So you have to kind of think about it a little bit and make sure that what you're doing is actually applicable to the scenario that you're looking at. And I think in a previous chapter, we looked at the Augmentations library. That has a whole massive list of them. And so it's pretty common to just look at the list and say, okay, these 5 make the most sense to me, so I'm going to throw them in and see if they're useful. So in the graphs they were showing that they actually, in some cases, slightly hurt the negative classification, the majority class, but it really helped the minority class, because we only have 500 examples of them. So if you create new realistic samples, it helps a lot when you're trying to make future classifications for it. So just something to keep in mind. Any questions on augmentations?
I don't have a question on augmentation, but I was wondering for non-image, based data sets, what is, I guess, the equivalence, or some way to, mess with the data, to add more towards it? What would suggestions be?
If you have like tabular data, there's a lot of different creative things you can do there, but for the most part, you just have to kind of simulate realistic scenarios, and it typically takes domain knowledge. So if you have one column and it's just a true-false column, and it doesn't actually make a significant difference to the prediction, you might want to just flip it back and forth, and you can make a new sample with both of those. And then in theory, when you're predicting on new data, you can just have that thrown in. Or if you have something that's multi-class and there's 16 possible features and I know these 2 are similar, then sometimes you can shuffle those in. But I think tabular data is a little bit tricky, because you have to do something that is realistic without changing the class. And that means that you already explicitly know whether something is a factor or not. So I think with tabular data, it's a little bit tricky.
For other high dimensional data, though, like natural language processing or audio files or anything that you need to do feature extraction from, those are the more ripe for things you can do for data augmentation. Like for text, you shuffle the order of the sentences in a document if the order is not relevant to the way that you're trying to interpret the entire document as a whole. Or you can even have a rephrasing algorithm to rephrase a sentence to mean different things, to augment a data set for a particular sentiment analysis or classification algorithm.
Yeah, I mean, a comment / question for me is some of these augmentations, so when you do a mirror image left-right, it's pretty much not adding any noise. Like you can do that perfectly without any loss. This shifting the image left or up by a fractional number of pixels, and then causing the image algorithms to interpolate what the new pixels should be, that's actually introducing a certain amount of noise into it. And then obviously the bottom one, literally adding noise, adds noise. So if you're overfit, then these could potentially save your your bacon, where it stops it from being overfit. If you actually have a high performing model, I could see where introducing some of these could actually reduce performance, because you're ultimately adding noise. They showed that when you just add noise and do nothing else, it actually hurt the performance of the model. Okay, but it was necessary for again, just there were so few examples of nodules that you know, the model was just memorizing, oh, this is example 17, so I'm going to predict it's a nodule, as opposed to saying, what's the shape, what's the size, what's the whatever other stuff it was looking at. So like I saw a thing on a certain kind of augmentation for NLP. And so they said, for example, you can swap words with synonyms. So you have a sentence that says, this book is really great. And then they changed it to, this book is really awesome. All right. And so again, if your model is having trouble, then I could see that this could get you out of the danger zone. But if you had a really good model and you start just doing arbitrary synonyms based on just some list, you could actually hurt your performance, because in some cases, they were talking about a person's great toe, okay? And that means your big toe. And so when you say the person's awesome toe, all of a sudden this doesn't really make sense, you know?
And most modern models that use an actual sequence model of your text will have that synonym built into the vector that they're using for the word already. So you're not actually improving, you're not actually augmenting your data much at all. You're corrupting it in some cases. Right.
So anyway, I don't know if I'm making a statement or asking a question or just sort of sharing, but like, certainly if you are stuck where you're overfitting, where you basically see that your validation performance is just horrible, it's absolutely worth trying augmentations to see if it can get you out of it. But I don't know that augmentations will always help your performance, is kind of what I'm getting at. And I think it gets at the root of why what you were asking, Tommy, right? It's not always easy to find augmentations that don't add noise. Just like a mirror image is almost like you have a picture of a dog and a cat, and you take a left-right mirror image, and it is still a dog, it is still a cat, and you've lost no data. And you're 100% certain your labels are still accurate. But you start doing these other things, and you just don't know that your labels are now 100% accurate.
Yeah.
Yeah,
it's interesting. We've been playing around with augmentation, and I don't know if other architectures do this, but there's this new thing called mosaic augmentation, in that they will take an image, and instead of having a cat, they will put cats all over, 25 cats in all different orientations on a single image. And it actually worked. I was shocked. It actually boosted us a little bit to do something like that. And in medical imaging, I wasn't thinking that would happen, but it did boost. And things like stretching and shearing, that wasn't very effective in medical imaging, because you don't typically see images with the shear or the stretch like that. So yeah, we had to pull that off.
Just want to point out that Ted's comment about the medical imaging being reduced in precision by the noise. That's if you're going to add noise to images, only do it if you don't have some other way of compensating for noise in your images, like with random dropout on your images, because that does it much smarter and much better. It spreads out the learning in the right way. It generalizes your model in the right way.
With these, so with these augmentation, to enhance your model more, is there a typical, like, oh, I'm going to add, 10% of the total images with noise to try this out? Like, I guess steps to kind of think like, how could I improve this with, this certain number? Because I know that's kind of hard if I say like, oh, I'm just going to add 100 images, but if you have like, a 10,000 image data set, that's really nothing at all. So just kind of curious on general tips.
I think it depends on the type of augmentation. What I've seen more recently, what most people do is they do some sort of generator where they just say, I'm going to continue iterating over this data continuously, and every 10th sample, I'm going to do some
Right.
augmentation of it. So you keep seeing new variations of your samples over and over again. It's not necessarily that what you were saying is you add a block of 100 and you say, here's 100 new samples. What you typically want is a continuous running new variation on the samples. But then on top of that, in terms of like what proportion, I think that's kind of similar to just tuning your dropout rate or something like that. It's kind of just dependent on how severe your problem is. So on the lift competition, I've got an augmentation I came up with, and I'm doing it about 10% of the time. And I haven't even tried other variations, but it was just very specifically, I see this variation, I want to simulate it some amount of time, so I at least get exposure to it. And it's kind of the same as the imbalance problem, where you don't want so much that you're oversampling your minority case, but you don't want so little that you're not getting reasonable exposure. So that's
Yeah, and I think
it.
I think the authors either explicitly stated or they sort of very strongly implied that if they were actually trying to get a medical imaging product to the market, and this wasn't just a book, then they would have much more rigorously looked to see which of the augmentations helped, which combinations of augmentations, how much you I think they might have done 50% on each of them in the example in the book. Maybe not the noise, but the other ones, the flip, the whatever, you know. And maybe you don't want that many augmented ones. Maybe you do 30%, maybe. And so they would have done, and I'm not going to go into whether it's an exhaustive, a grid search, a, you know, whatever, but basically they would have much more rigorously tried to see, you know, where the optimum was. And so then you might find that, you know, Earl, the shear doesn't work because they're round. And so when you shear it, now you have, you know, ovals.
Yeah. The problem is we have limited computing. I want to fast forward like 10 years where I could just rotate a dial and see instantly what the effect is going to be, but we're not there yet. So you have to wait a few hours and see what happens, and then try some more and try this and try that. Yeah.
So that actually has been one of my frustrations with Kaggle, is that sort of over the summer, a lot of the competitions they had were so big that it would take me overnight to train. And so to just do a very minimal grid search of like a couple of different augmentations and see which ones work would have taken me, you know, 20 different tries. And that would have been 3 weeks of computing, just like that, not even doing anything else.
So I have a question. I don't know if it's appropriate for now or future discussion, but one of the things that I'm always really interested in is interpretability, right? So we have this system that we're feeding all this data into. It's going to make predictions, but we don't know what it's basing those predictions on necessarily. And an example of this is I was reading a paper earlier this year on medical imaging, neural networks for medical imaging that they were doing. I think it was at Mount Sinai Hospital or something like that. And what they found is if they brought in images from a different hospital, the system was god-awful at doing the interpretation. And part of what it turns out was the system had learned that if it came off of a particular machine in a particular hospital, that chances are that this person had whatever they were diagnosing, because as a general rule, you only stick people in there that you already suspect have the condition, right? Stuff like that. And it had actually learned to be able to discriminate one machine from another, because at one hospital they used those little tags that they put to show whether it's a left or the right side, whether, all that sort of stuff. And so those little blocks were slightly different between the hospitals. And so the thing had learned to be able to interpret those things, to be able to figure out what hospital it had come from, et cetera, et cetera. So at some point, I'd like to have a discussion about interpretability.
Yeah, and it even gets worse because, in say like ultrasound, there's really kind of an art, and you have two sonographers that image slightly differently, and you could train on one sonographer, and then the way they train on the other, that even affects it. So it's a tough problem.
Ryan, what was that you were showing?
I was just showing my current run that's going to take 40 hours, as Ted was just talking about how it's annoying that you have to sit and wait so long. And
that makes you have to think harder about what you're going to launch.
That's exactly what it is. It's an interesting exercise, and it's all about, I have a limited amount of time and I'm trying to make the smartest decision. Sometimes it's, I need to explore a new path and see what direction do I go from here. And then other times it's, I think this is going to be the best and I'm going to exploit it a little bit and just take a little small gain in this direction.
You know, we went through this with photography, right? So a few years back, when digital photography was just starting, I took some lessons with a really well-known photographer who'd actually been an army photographer. And he was really insistent on us that even though it was digital photography, that we still needed to treat it like it was film, because he said, you're going to waste an inordinate amount of time taking so many pictures and then having to filter them and then having to decide which ones to process, et cetera, that you're better off pretending that you only have 36 exposures and making each one count.
Sorry, I needed to unmute. Stephen, you mentioned interpretability, and I was actually thinking, Ryan, that this online book might be something that we do, put it in the queue. I found that it's pretty good, and it's not super advanced, so people who don't know anything about interpretability, it's okay for beginners.
I presented on that a long time ago, actually.
I think we looked at one chapter from this, didn't we? Or
yeah.
One particular.
When we were looking at Lime and Chap.
Oh, that's right. Yeah, you did the Chap talk.
Yeah.
But so maybe we do the whole thing.
Mm-hmm. Yeah, that'd be an interesting one.
Yeah, I'm very interested in that, actually. When you talk about the FDA and medical, and how do you explain how these systems are working? Yeah, it's very interesting.
Yeah, I agree. In my work, there's a lot of non-machine learning people, so it's always about explainability. I'm like, deep learning.
Yeah.
At H2O, I play no part in this. I only even vaguely know these people, but I know that they also just released this ebook on responsible machine learning. And so this is the guy, Patrick Hall and Navdeep and Benjamin, they've been working on our explainability, interpretability, and responsible machine learning stuff for a long time. And so they have a pretty deep understanding of all of the different techniques. And they're also trying to, so some of the stuff, it's like, we can understand this, but then they're trying to extend it into how do we actually act on these understandings, and how do we make it so that we're removing biases and different things like that. And so that's kind of what this ebook is getting into. I haven't looked at it. I can't personally vouch for it, but I know that these guys are really knowledgeable. Just thought I'd share that as well.
Yeah, and the whole paradox is, what does it mean to test a neural net model? I mean, how do you effectively test a neural net model? It's pretty complex.
Not so much test, but explain to a non-machine learning person what's driving the insights, right?
Right.
So at this point, I don't have anything else to share in regards to the book. We could, in theory, look at the code, but I don't think there's really that much interesting going on there.
Hey, Ryan, one question I had, I was planning to look at the code, but do you know if they did all of these augmentations on the GPU? I think they did.
I'd have to look. I haven't seen very many augmentations done on GPU. It tends to happen on CPU. I'd have to look though. It's
Yeah.
fairly rare.
So just for the audience, like the snippets that were in the book, they were all PyTorch tensor code. So it's just a question of what. So the tensor, the images get loaded from the cache, and they're in CPU memory, main memory, and then at some point you do 2 GPU or 2 device, you know, and they get moved over to the GPU if you have one. So the question is, do the augmentations run after you've loaded it from the disk/cache and before you've done 2 GPU, or does it happen, you know, after you do? And I was just curious because typically, if you're doing all of your heavy matrix multiplies on the GPU, actually it's the bottleneck, and so you have sort of free cycles on the CPU. So rather than using even more of your GPU resources to do your data pipeline, you would typically have enough CPU resources to do your augmentations and still be fast enough to serve the images as fast as as the model needs them. I just didn't see the authors mentioning explicitly, because I just saw they're like, line 234, here's where we do the flip, you know, and it's like, okay, but is this before or after?
So to do that, to make that happen, you would just have to do the pre-processing in Python so that it would not use the device. Is that what you're?
No, you can actually do it in PyTorch on the CPU. You just have the code appear before you say my image, which is in a tensor, .to device or .to GPU.
Oh.
So in other words, they're loading it. Not everyone's pipeline is going to look like this. This is the PyTorch book. So basically, as soon as they load the data, they're putting it in a PyTorch tensor. So every operation they do, including these augmentations, they showed you how you could do them in PyTorch. I think that's a good point, Hobbs. A lot of people might use CV2, they might use whatever, and they would actually do their augmentations before they put it in a PyTorch tensor.
So I'm presuming this is where the code is, and it looks like this is happening on CPU, purely based on they're making this tensor and they're casting it to a float, but they're never sending it to GPU, and all of the data has to be present on the GPU for them to be doing any math on it. So I'm figuring it must be done on CPU first, and then they send it to GPU after. Yeah, and they say 2 CPU there.
Yeah, we should monitor the CPU usage.
Yeah, I tried just taking a peek, and for whatever reason, my CPU usage, I only had a tenth of the data, but my CPU usage was nothing. It was like 3% while it was training. But it could just be because my GPU's not all that fancy, and so it was just, you know, taking forever just to process one image. And so my CPU's like, oh, did the augmentation, got nothing else to do. I'm just twiddling my thumbs.
Yeah, I've been struggling to figure out how to properly get utilization out of everything on this problem, on the competition. So this is sitting down at low utilization. And then if we look at, these are the 2 tools that they showed us, so I figured we might as well look at these too. So on, I don't know, I have to look at it more closely, but I have not been able to get good utilization from the GPU, no matter what combination of hardware I try. There's partially, I think, a bottleneck in terms of the disk speed, but I'm already using the fastest available, basically. So
yeah, you might be surprised. If you have a hard drive, it will be faster on bandwidth and throughput, but slower on seek time. So it depends on what operation you're doing as you're reading from disk, whether you're like using an H5 file where you're seeking to a particular location versus whether you're just reading an entire file into RAM and doing all your augmentations. I don't know.
Yeah. I've tried various different combinations, and I've been trying to figure out what exactly works and what doesn't. So on this specific case, this is probably too small of text. But this is an NVMe SSD, so it should, in theory, have the fastest possible reads and writes and IOPS and everything.
That's what I'm saying. Is an SSD does not have the fastest throughput. It's surprising, but a hard drive will actually have better throughput if your stuff is sequentially in a block rather than scattered around.
Yeah. But the other thing that I have been struggling with is when I first turned on the system, I had 16 iterations per second roughly, and now I have 7 or 6 roughly, and I just restarted the system, so I have no idea what is causing this to be half as fast as it was yesterday. So that's something I've been toying with.
Did you version control?
So there is no code change. This has just been running continuously. So it ran continuously yesterday, and then today I restarted it thinking, oh, maybe it just accumulated something in the cache that was bad. And I restarted the system and then started it up again. Same exact code, no changes or anything. So
was it a warm start on the model training, or was it a fresh, clean start with 0 weights?
It's been continuously training the same model essentially. So it's got a set of weights that it's updating and saving a new version of.
I'm trying to figure out what changed.
Are you doing any type of logging, Ryan?
I am, but only after I finish the training. So it's not anything interspersed in here.
Nothing per epoch or anything like that?
No. Yeah.
Okay. Because I was just going to say, you want to make sure that you're doing those in a whatever independent way, you know, so you're not appending or doing something that could be expensive.
Yeah.
This is minor, but if you do fixed width numbers in your printout for that status on your your TQDM bar, that will dramatically speed up the display delay in putting those characters on the screen.
Yeah. Is that directly in the TQDM call?
Well, how are you displaying that loss within TQDM? Are you defining that string that it's displaying for that loss, or is that defined by somebody else?
So that's.
Yep. So you just put a colon inside of that curly brace and say, I think it's like 0D or 05D. To format specify the fixed width of that loss dot item.
Yeah. Okay. So it's just the formatting of the string, really.
It would just keep your bar from sliding all over the place, and all the updates that requires, and all the math that's required to do that update optimally of your screen. It's not much. I imagine it wouldn't make any difference at all.
If we have nothing else, maybe breakout rooms if we have interest.
Yeah, that sounds good.